Hi, welcome to Math Fun. Today we are going to talk about an infinite series. This one is n factorial over n to the power of n. So first question you may have is, does this series converge? And if it does, what is the number? And that's what we are going to do today. So here is the infinite series. As you can imagine, n factorial will approach infinity a lot slower than n to the power of n. So it kind of suggests you that this should converge. But how do we prove that? We will have two ways to do it. The first way we're going to do is we're going to use what we call a ratio test. Okay. So what does a ratio test tell you? Well, if we call the series an, and if you can prove that the limit when n approaches infinity of an plus 1 divided by an, in fact, you can take an absolute value of it. If this one smaller than 1, then the series an's, the sum of it actually, will converge. If it is bigger than 1, then it definitely diverges. If it is 1, then we need something else to determine that. So let's see how it looks like. Now obviously in this case the number is positive, so we do not need the absolute values. So what we are going to do here is going to do an plus 1, so that means n plus 1 factorial divided by n plus 1 and n to the power of n plus 1 over n factorial over n to the power of n. So this is a sub n plus 1, this is a sub n. So we will try to eliminate something. So first of all, we can go over here. As we all know, a plus 1 factorial equal to n plus 1 times n factorial. So n factorial can be eliminated. And that will leave us with n plus 1 out here. Oh, as a matter of fact, we have an n plus 1 to the power of n plus 1, don't we? So we're going to eliminate that one and make it 1. And over here, we have an n plus 1 to the power of n left. And remember, these one have been eliminated. So we're going to have 1 and n to the power of n. That will be n over n plus 1 to the power of n. Now this whole thing will approach 1 over e, as a matter of fact. And if you say, how is that possible? I could not see that. Well, we will know the definition of e is in fact 1 plus the reciprocal of n to the power of n, isn't it? And this equal to what? This equal to n plus 1, sorry, n plus 1 over n to the power of n. Now you look, these two are reciprocal of each other, isn't it? And this one approach e. That's why this one approach 1 over e. And we know e equal to 2.711828, etc. So this one definitely smaller than 1. And that tells you that the sum of this infinite series converge. And that is the first method. The second way to prove that it converges, we're going to use what we call a comparison test. Now, how to do that? If we have two series, so a series of an and another one bn, okay? If an's smaller or equal to Bn always, and the sum of Bn converge, then An will converge. That's how to do it. So in other words, we need to find a Bn that is bigger than this number, and that one converge, then we know this infinite series will converge. So how do we do that? Well, let's try it that way. We have n factorial divided by n to the power of n. Now n factorial by definition equal to 1 times 2 times 3 and continue, and then until times n easily, right? N to the power of n, that's simple. That is n times another n times another n and continue times another n. So, well, we can cancel the n out here, can't we? And what we can see here, though, is that all the numbers before it, we can pair them up. They are smaller than 1. Over here, you in fact have an n minus 1 here, don't you? Still over n, right? So all those numbers smaller than 1. So what we're going to do is we're going to just choose the first two numbers, okay? So smaller than 1 times 2 over n times n. All the other ones smaller than 1. That's why we have a smaller size here. And this is 2 over n squared. Now we should all know, is the infinite sum of n squared reciprocal and n from 1 to infinity converge, as a matter of fact. Now, and that's why we found Bn, one of them at least, and because the Bn here converge, An will converge. Now, if you do not know how to prove that this one converge, let me show you in the next slide. For this one, it's very straightforward. Anyhow, we just proved that this series indeed converge using two different ways. Okay, so now let's show that this infinite series actually converge for each sum. So how to do that? Now this one is pretty easy and we do not take any test. Okay, so let's do this. N square reciprocal. Well, the first item is obviously 1, so that will give us 1 over 1 square plus 1 over 2 square plus 1 over 3 square plus 1 over 4 square, etc. Right? Now we're going to take the first item, just call it 1 because it is 1. The next item we're going to do is that we're going to say, you know what, this one is smaller than 1 times 2, and because of that we have to erase the equal sign and change it to a smaller sign. Isn't that right? And the second one over here, we're going to change it to 2 times 3, and then we're going to change this one into 3 times 4 and continue. Now as you can see though, is that the number on top, this one is always smaller than this one, this number smaller than that one smaller than that one, continuously. So that's why it's always a smaller sign. And this one equal to what? This one equal to 1 plus, now this one equal to 1 over 1 minus 1 over 2, isn't it? Plus this one equal to 1 over 2 minus 1 over 3. And that one equal to 1 over 3 minus 1 over 4. And you can just continue on that way. And now what? Well, now we will realize is that this one can cross out, that one can cross out, and obviously this one will cross out and continue on that one. So that tells you is this one is smaller than 2. So they tell you that the sum of this infinite series has a upper bound, and because it's a positive series, that means it actually increases monotonically. So there is a very famous and very useful theorem called the monotone convergence theorem. When it increases monotonically and has an upper bound, then definitely has a limit. So that's why we know this one converge. Of course, what would this series converge to? It's a big problem in history actually, and it turns out that it equal to pi squared over 6. I'm not going to show how to get to this one here. Now, our hero Euler was the first person actually demonstrates this fact. So that's how to prove the reciprocal of n squared converges as the sum. Okay. Now, as you can see so far, we have proved that the original series converges using 2 different methods. So naturally, you're going to say, hey, what would that number be then? Can we, just like Euler did, have a analytical answers? Well, it turned out that this is probably not the case, because, well, I tried many times and I could not find a way to do it. And you may say, oh, I know that because you definitely not Euler, so that's why you could not do it. Yeah, I accept that. Very, very far away from him. But I also Google over the internet. Nobody talk about analytical solution. So my suspicion is there is none. So I decided to use a very short script of Pythons to do the calculations and to see what the numbers ends up with. So over here, I call it I instead of n. As a matter of fact, when I equal to 1, obviously the sum is 1. And then when I is 2, it's 1.5. Everything looks good and the number increase. When I equal to 7, as you see, we already have the first 3 digits correct. And it increase, but when I equal to 39 and higher, Python in fact will give us the same number all the time. So it does tell you it converges, and the number is 1.8.7985 etc. I really do not know what that means, but this is the sum of the infinite series for I n from 1 to infinity, and it is n factorial over n to the power of n's. I hope you have fun so far, and if you like these videos, please make sure you like and subscribe. See you in the next videos. Bye bye.